one that's sort of constrained on certain space, and then use data. So like, just grab them both and see. Same thing. Makes sense. Thank you so much.
Okay, guys, should we continue? Because lots of stuff to talk about. So before continuing with the whole topic of deep learning, which we haven't started talking about deep learning yet, so we will wrap up. Just a reminder that like most of the data we talked about today falls in the case of remote sensing and coarse resolution observations. Not necessarily coarse, but remote sensing observations. There is also the situation of in situ, and the key there is that they are very localized for very high quality. And then you also have numerical weather models, not necessarily weather, numerical models. So if you have an understanding of the physical processes that characterize your phenomenon, what you can do is you can use this physical process, initialize this physical process without observations, and then you run this numerical model to do some prediction or retrieval or estimation. The problem with that is that all very capable and numerical weather models are the things that we use every day to do weather forecasting, so they're extremely powerful and accurate. They're expensive, right? So you need to have performance computing, running the system because it's usually defined as a differential equation that we have to solve them one step at a time. And if you have limited flexibility, so you can design the system that if you do 3-day prediction, there is no way of use that to do the 4-day prediction, right? So it's like very nicely well-organized systems that they have all this data encoded there. So one of the sources of data that we use in the context of the model is called the data assimilation framework. So in the data assimilation framework, what we're trying to do is say, okay, so I'm going to get observations from satellites, I'm going to get observations from drones, I'm going to get observations from in-situ sensor networks or local weather stations, and I also have the numerical models. Can I integrate them all together? So when you do typically take satellite data which are level 4, for example, what you have access to is what's called the data simulation program. So data simulation is the idea of fusing the different types of observations so that you are consistent with the physical model and observations at the same time. So it's fantastic because we can have the fact that we have some observations not all the time with a lot of physical measurements and noise. And it's a way of indirectly encoding all this information with the physical model. So it usually leads to the analysis data and data sets. So data simulation is another type of source. And one of the ways of saying I have a deep learning model, but I want to make sure that it's constrained by a physical model, physical laws, is by using this. So this is one of the stuff we investigated. If you have a data simulation model, which is prestige, mathematical physics framework optimized for every location. If you have this, but it's coarse resolution, so you can imagine having this as a baseline and apply the deep learning model to increase the spatial resolution or the temporal resolution. So my idea, my opinion is don't throw away mathematical physical models that exist there. Try to see whether you can integrate it with the data that you have or the system you're trying to design so that you get the best of both worlds. But still, right, so we're trying to talk about the whole idea of machine learning. So the idea is that you have data and labels and you're trying to do the prediction. So these are remote sensing, but it's very remote. So you try to identify the state of the galaxy. This is the assumption that we have two types of data. And it's interesting, I give this example because I work in astrophysical data, but also because it's like, how do you actually get the data? Do part, go measure something. So, how do you get the data? So, number one, expert users. In remote sensing, I'm having observations, I want to learn how to classification, but I'm going to use the data to learn how to classification. someone else, an expert, sit down and use a magnifying glass and say this pixel is forest, this pixel is forest, this is forest, this is forest, this is this, and in the last our classification. So expert user is for idea. Crowdsourcing, so this is another approach. So instead of relying on a small number of very high expert users, you resort to a really big number of not very expert users. So this it's interesting. This gives me an abundance of physics, and they had a lot of observations from Harvard, and they want to identify whether this matters or this matters. And it was a huge amount of data. So what they said is like they make it public, and they ask people to go and classify your eyeball there. You must say whether they think that it looks like a spider or it looks like a pizza. And it's very interesting that if you have one observation from an expert versus 5 observations from one expert, you get pretty much similar performance, right? Because you can average things out and then you can sort of get compared. So even a relatively big number of non-experts can be quite useful in updating this data. Or you can have other situations like remote sensing. I'm walking around and I identify this case of this disease, so I update that, and then my remote sensing system try to identify diseases. Right? So crowdsourcing and other so I can have observations that are force the solution, but are all the time, and it's very difficult to get around from there. But on some very specific instances, I can have a different instrument that provides very high resolution observation or very nice spectral data. Observe the same region, so I can have like 2 types of instruments looking at the same region, at the same area. So I can assume that one is the input and whatever information you get from the other is the ground. Right? So this is a scenario where you have multiple instruments and each one has a trade-off. And you try to see whether you can use leverage the capacity of one instrument in order to enhance the capabilities of the other instrument. So this is another getting for example, in land cover classification, the baseline land cover maps for the global land cover maps come from models. So you start from an automated system hypothesis and then uses. So you start from this, and then you just perform expert analysis and identify that. And the other situation, which I think is the most fantastic one, is if you have a neural network or a deep learning model, and you don't have ground rule, see if you can pose the problem as that of a forecasting or a time series analysis. Why? Because you can use the number of training examples. So if I can say that I'm trying to predict what's the weather today, tonight I'm going to get the ground prediction, right? So I can do that historically, I can take all these time instances, and for every time I do a prediction, if my prediction is consistent with what I've done, I can say, you know what, my model is doing well. If it's not consistent, I can say that my model is not doing well. So if you have time, you should try to capture this in modeling your data. We talked about RNN and LSTM and how they can capture that, but also try to capture that as a problem formulation. Try to see whether you can use that and you get like ground, for example, as I said, forecasting. Any question on that? Okay, so deep neural networks, right? So I think we're going to focus now somewhat related to the real biological neural networks somehow. Not that I think most important thing that if you think about this slide. So this slide talks about the biological neural network in the brains of humans and elephants in this case. And it says, what's more important? The number of neurons. Neurons are the cells in the brain that does actual communication, the thinking. So if you go and just count them, you see that the brain of the elephant is much more this type of neurons, this type of central to thinking compared to human. So you would say that according to this study, the elephant is significantly smarter than the human. But what is found itself is that it's not the number of neurons that is important, but it's how they are connected, right? So connectivity in the brain, in the systems, in life, everybody seems to be the most important and critical trait in getting something interesting out. Right? So in this case, what we end up seeing is that the electric one more connected neurons compared to the that's the interesting side. But based on this observation of biological neural network, we find an artificial neural network. So this is a standard plot of what it looks like. It means that I have a system that all these demonstrate indicates to someone that I'm doing a neural network and not support vector machines. I have inputs and I use this, circles there to demonstrate that I have inputs. I have circles there to demonstrate that things happen in the middle of the network, and then I have circles there to demonstrate that things happen. So this is just a visualization. It doesn't provide anything. But it's just a way of saying that, what, I have my input, things happen in my network with this input, and then eventually it happens. Right? So the process of training in a network is that you have training data, just training data is observations around the truth. So in this case, it's 100 digit recognition. So you have 100 digit, and then you have the digit, the computer digit. So this is the image of 4. So 4, 0, 7, 4, all these numbers. And what you do is you try to take all this data so that when I get through this process, it's called training, which is what humans do, train. So you see example, to predict the value, and then you have the ground truth, then you can say whether I'm good or not. Once you do this training, and you're done with it, then you apply to the process of testing on inference. So in inference, you're given an input, and you try to identify what this is. Say, for example, you have numbers, you can imagine with images of large number classes like that. So it's a similar idea. Right? So in training, you have the input and the output together, and this is given to the system. In the validation, the inference stage, you just take the question is take this input and tell me what it includes. So the architecture is like that. Right, so you have input, output, and then processing happening in the middle, and then everything all of this design, sort of responds to biological neuron, not necessarily, practically, mathematically, it takes a general combination of the inputs. So effectively, you try to encode this function here, and there is a non-linearity I'm talking about. So it's this logic here, it's like a circle with lines, simply corresponds that this logic corresponds to this function. So you're going to take things that are connecting to you, you're going to multiply it with some numbers, you're going to take the linear product, the linear combination, add some numbers, apply it to the function, blah, blah, blah. All this happens to anything. Right? So each of them is this type of function, but with different numbers. So these numbers here are the ones that characterize each individual component there. So this one is the linear combination of the inputs. Right? So it's not that complicated as a process. Right? So how do you expect the system will be able to produce interesting stuff just by taking linear combination of inputs? And that's the non-linearity. So this F here is the non-linearity. So it's a function that can be a linear, a logistic, or a rectified linear unit. We're going to see example later of what it means. And what it does, it introduces one step of non-linearity in modeling the data, which is fundamental and necessary. And then you have this system that takes the inputs from the product take out. So this was the perceptron. And then they said, okay, so instead of having one layer of taking the products, maybe they call this and take new inner products. So they come up with a multi-layer perceptron. So this is the same as before, but every node here takes a different linear combination. So they started from a single node to multiple nodes. So they started using this notion of hierarchy. And then this logic, right? So this is another architecture. So this is an architecture where you have the inputs. Each node here corresponds to this linear product, linear combination of values, non-linearity. And then what you get the output is you get something that is typically 0 and 1. 1 corresponding to the node that is associated with the linear before. And one of the things that deep neural networks make them so interesting, make them deep, because this is neural network. This is a neural network. What makes them deep neural networks is that you can have a very big number of layers like that. So a very deep architecture. And the reason why you want to have this deep architecture is because this sort of automatically encodes feature characteristics. So you start from things that the system automatically identifies during the beginning, which is like black and white squares and things like that. You progressively move up until you go to the very top of this hierarchy, where you find features that are very semantically rich, right? So you find faces and part of the face and so forth. So when you put this hierarchy, you start from stuff that are very low level characteristics like frequency type or Gabor type characteristics, and then by itself the system will progressively extract more complex and semantically meaningful features. So again, by itself. And nowadays, you can have all these different networks and architectures and much more on that. So what's happening here is, I have this system now, all right? So all these images just tell me that there are different ways of connecting the different individual nodes here. And what's important is these values here, right? So these weights, this is the critical thing. So how can we learn this way? So this is the process of training, right? So as we said, the training, the whole idea is to determine the values of these weights. So you do a linear combination with some weights, find those weights. And once you do that, you apply these weights to the input. So you have a situation where you have the input, the neural networks try to apply these weights and extract some features, and these features by themselves will lead the system saying that, this is the digit 7 or digit 8 and so forth. But training neural network is this iterative process. So step 1, get a bunch of data, inputs and outputs, you have to subtract those and the associated labels, the same kind of those. And then after that, apply with this process. First, go take the data, apply them through the neural network, and get some predictions, right? So these predictions here is like my system is going to say, okay, so this is the image. So those are pixel values. So you can think about this image as a very big matrix of values. So you have a very big set of numbers, and take these numbers and somehow magically I put them in the neural network, and then magically this thing will produce a vector that is in all elements of the vector 0 except for one case which is not 0, which is this case, and I assign that if you have one in the first case that corresponds to the image of the dog, if it's a 0, the second case is the image of the cat, third image of the bird, and fourth image of the fish. This is my assignment. So when I give the system, when I try to let the system play, I say, you know what, you're going to be given this image, and you should try to estimate this, produce this something, where the second element is 1, which for me that means a cat. If my system produces something where the first element is a 1, which is a dog, that's an error. And that's the whole idea. So this error, how can you make this error go to 0? Because if you can make this error go to 0, that means that the input and the output are exactly the same. And you do that through defining the loss function. So the loss function is the most important thing. When you design a network, the important thing is what is the architecture, what is the input and the output, and what is the loss function. The loss function will tell you how do you measure the quality of what the system is doing. So if I have a system where you are taking an input, an image, and I'm trying to estimate a continuous number, that's what I'm taking an image of the human face, I'm trying to estimate the age of the person there. That's a continuous number. So when I'm trying to estimate a continuous number, the loss function that I need to use is root mean square error. So the root mean square error will say, I'm giving you this image. This is the first case of the person. So you say that the image age of this person is 37. You send 38. The difference between 37 and 38, that's the error. Keep that there. This is the situation when I'm trying to predict a continuous number. I might have a situation where I give an image and I'm trying to say whether it's a cat or not. So in this case, it's not a continuous number. You should say it's either this node or the second node. This is the node and this is the cat. So it's one or the other. So in this case, the loss function is the categorical percent. And now, but these are the fundamentals. This is when you're trying to develop a deep learning system in your problem. One of the things that you're going to very soon have to face is what is my loss function? Because my loss function is going to say how my system is going to behave. And this is an endpoint and a start point. So if you think about how to formulate the process, you're going to end up with a loss function. And this loss function will tell you what the system will be able to produce. So this kind of loss function, it does that. So it should predict something that looks like that. So this is for cats, this is for dogs, this is for planes, this is the one we use, right? This is the not correspond to that. And this is what you get, right? So ideally, this should be the same as this. There is an error. How do you measure the error? Through this. Right? So if you're trying to get a specific number, you can take the difference between those numbers and you're done. If you're trying to predict a class A, in which case you have data that looks like that, you cannot just take the difference. You need to take something more involved, and this is the something more involved. So the predicted value versus the current value and the loop. So this is the categorical entropy, and tells how well this distribution matches to this distribution. So if you get 0, that means that the prediction and the ground are exactly the same. So this is the error. This is the error. So to the data, I have the outputs, I compare those outputs to predictions. Depending on my setup, I'm going to use the appropriate loss function. So I have an error. What do I do with this? I do back propagation. What does it mean to back propagation? I do gradient descent. That's why the standard technique for training deep neural networks is stochastic gradient descent. Gradient descent, which is the very fundamental algorithm for solving optimization, says that if you have a set of parameters and you want to update them, make sure you find this loss function, you find the gradient of this loss function, and when you want to minimize this loss function, you want to minimize the error. That means taking the gradient and saying the gradient equal to 0. Right? Because this, when the gradient becomes 0, this is the minimum of the function, and since it's a loss function, this is the minimum loss, so I'm not losing anything. Right? So when I reach this point where the gradient is 0, this will stop taking these parameters. Yeah? While this SSCS exists, or when I'm still making mistakes, my gradient will point towards the direction where I'm minimizing mistakes. Right? So you better minimize this with respect to the gradient vector. And since it's a complicated function, so because you're multiple layers doing stuff, you need to do something which is trivial. In this instance, use the gradients along the different parameters. Right? So depending on the different inputs or the different parameters, I can take lambda, and decompose it to the partial derivatives. So if you have the partial derivatives and you have a complicated function, what do you do? Apply the same. So the same rule says we verify the gradients, but the gradients are not going to be gradients all the way they could just complicated functions. So you have functions of functions, so you verify the gradient of these composite functions. What do? You apply the chain. So the gradient of the composite function is the gradient, the product of the gradient of the different ones. So this is calculus 101. Nothing fancy there. This idea is that you have a complicated function, but still we're going to minimize this, so I'm going to take the gradient, so gradient descent, and it's complicated because there is hierarchy, so I'm going to use chain rule with gradient descent, those two pieces together are called back propagation, and this is our rule, right? And then if you don't really know the data, but you do the small number of data, it's called stochastic gradient descent. So stochastic gradient descent, you don't find the gradients for all the errors that I did. I just take a small batch of predictions. I found on this batch the errors, and I take my gradients for all the same. And then there are different optimizations how to get there. Off the self, now you can use that like most of the time it's not going to make it significantly different in terms of performance in what you're trying to do. So in this case, when you have stochastic gradient descent, it is to implement other characteristics and other methods. For example, I think we use algebra. Other techniques might produce something better, but again, you're not gonna the regime where the difference in the optimizer will make a difference in your performance is like trying to beat like the state of the art. If you're just setting up a system, you're not going to make a lot of mileage by changing the optimization. So you pretty much do the same thing because that's what they're supposed to do. And you can see that, right? So you start from the initial point, and all of them try to find this minimum of this function, and all of them eventually converge to this minimum, faster than slower than and it didn't know, but in any case, it's doing pretty much the same. Any questions on that? It depends. I didn't use this, but it depends, and it's not going to make a big difference. So there are other things that we make complex faster. But they're in the levels there of the same. And what's very important when you try to train a deep neural network is this type of care. So you start learning network. I'm trying to minimize those functions. So I should expect that the more time I give the neural network, try to minimize the neural function, train this, apply this gradient descent, I'm expecting that this loss, this error will go down. Why? Because I'm trying to minimize that. So what you get is you get situations like that. So you start from the gradient steps, you think about the gradient steps, says the direction to be doing the gradient steps. So how many steps you take the gradient steps. So those are called box parameters for all days. So you start to think the beginning of making mistakes, I'm making steps, and I'm getting a better performance as I move forward. And this is what happens in training. So I'm getting better performance. And the reason I'm getting better performance is that my system is more able to express and move the information in my data. So this is what happens. So you start with something that is not very close, that's very captured in the distribution of data. then you eventually do something that is much better in the data, and then you end up something which is like perfectly fits the data. And that's fantastic. It is fantastic for the training set, but the question is not how the system performs the training set. This is like, you know, making the system a geek, I don't know, not geek, it's overloaded. Like making the system like too focused on a specific set of examples that you use. The thing is, a system will represent another image, another example. So this is the testing error, and this is what you have when you apply overfitting. So in the beginning, your system is trying to learn more stuff, so it's going from this one, which is a really bad way of explaining the data, with this one, which is a fantastic way of explaining the data. And then once you keep moving, you get in a situation where you're feeding too much of the data. So whenever we find something here, the whole system fails. Right? So in this situation, if I was talking about here, it would be very, very close to this line, so it would be okay. In this situation, if I get about here, because the system is so much feeding all the data, it's going to do something that's completely wrong. So there's a sweet spot, there's a trade-off where you have the system, it's becoming better and better, and at some point on, this extra effort does not translate to better accuracy. So this is the problem of overfitting, so making the system more sensitive to training data, and it is to be avoided at all costs, right? And this is the thing that I'm interested in. So this, the blue here, the data, this is a nice proxy, this is a nice plot to show you advisor, things like that, but it's not what's important for the system. What's important for the system is the red. And the red here, you can see that it's not monotonically decreasing. So there's a switch there. So I should stop here. At this point here, my system is robust enough to do the best we can with testing data, but it doesn't become overfitting to eventually veer off any flexibility that I do. Right, so very, very critical to capture this notion of underfitting and overfitting. And wrapping this up, I mean, this was still the first hour session anyway. So I was why the whole thing in the daytime, those two become really fantastic together. So a classical algorithm will work better with less data, but with more data. This is the simple learning models shine with more data. The fact that you can think with different applications, and you see this is a progression over time of going from 0 layers to 150 layers, and the this case goes down, so the performance goes up. So then we can have much more uses of dependency in the data from more complicated networks, and then you have more computational power, right? So GPU computing, cloud computing, all that stuff is extremely useful for getting this information. Any questions or thoughts or ideas? Yes.
Yeah. Can you go a little bit deeper or just do another round of explanation on the process of that propagation? Because I feel like
so we're not going to delve into that. There are a lot of tutorials in back propagation, so you can see around. So I'm trying to keep it, So the thing that is very important for you to understand as a designer is the loss function. So this is an option, right? So you have like different loss functions. Which is the best loss function for my problem? So this is the number one question. Once you decide that my best loss function for my problem is this categorical cross-sector. Why? Because my problems are layers, and I want to find things like that. So this is the corresponding data that we use. How do you get grades from this loss function? And how this grade is propagated through the network is something that we in general don't care about because the system does it by itself. It's a process called auto-differentiation, and all neural networks libraries do it by themselves. So you design the network, and the system will by itself define, okay, so this is how to do the backpropagation. What is important here in the backpropagation is what is the loss function. So this is important, this will change that. And the other thing that is hard is this end, is the learning rate, which sort of controls how fast the system will move towards minimizing this loss function. And so those are the two things that we should be more interested in. How do I define my loss function, and how do I define my learning rate? The optimizer that I use, not that critical. How the system is going to do the backpropagation on the neural network itself, given the specific architecture, as long as everything is linear and differentiable, the system will automatically do it. So you don't need to worry about this. Unless we're going to do research on this topic of optimization. So as a designer, the loss function and the learning rate, those are stuff that you need to control and define. How to do the grading descent and how the autocad will apply. It's part of it's automated, so you don't need to care about that function. Yes.
Feeding there any way to avoid overfitting?
Yep. Yes.
Is there a constant A for everything, or is there a constant across all of the comps?
There are two options. So when you start the problem, let's say, still like I will use them in deep learning or someone try deep learning today. I will start with deep learning. So what we say is start with deep learning. Things that we're going to be talking about there are fundamentals. In this situation, the learning rate is just one value that we fix there and we put it there. 10 to the -5, you leave it there. Now, obviously, if you play with this parameter, you're going to get faster performance. Right? So you're going to get better performance faster. So you can do that automatically. So you create a schedule that will automatically adjust the learning rate. But now we're going to do a lot of detail that is not necessarily obvious how your problem translates to a specific scheduling scheme. Right? So it's not, so I'm going to do like that with the specification. Which scheduling should I use? I don't know. And I don't think there is any one that fits the data. So this is a lot of trial and error. So for this trial and error part, leave it towards the end. Like start the stuff, like I'm going to put a very small learning rate and keep it there. And when eventually I reach a point where land like this 0.2% increase in performance because I need it for my problem, start playing with this parameter. But before that, I'm not going to do it. Yes.
One of the practical problems in machine learning is
We're going to talk about this towards the end. Last situation when you have a lot of coming from one class, but very small from another class. How do I do that? So, part B. Discriminative. So, discriminative model is AAA classified. So, as you said, when you try to find when you give an input and you try to find the continuous value, this is called regression. When you try to put it in a specific class, it's either one or the other. This is the classification problem. So, this is an example of the temperature. And to do that, we talked about specific neural network architectures, and the standard neural network architecture we're going to be talking about is the convolutional neural networks. We're going to dive into that, and the recurrent neural networks. Convolutional neural networks are fantastic for stuff that are like images. Recurrent neural networks and the variants for stuff that is for time, audio or time series in general. So a convolutional neural network looks like that. So what is like, reconstructing this image? What does it mean, this flow diagram? It means that you start from an image, and then you somehow take this image, and then you do something to regions of the image, and you create multiple intermediate images, which are called feature maps. They are called feature maps because they are somehow reminiscent of the whole idea of features. They are not explicit features, they are not like DPI or anything like that. They are like numbers and characteristics, but because they have this notion of extracting information from raw measurements, we're called features. So we're going to apply this, and we're going to apply multiple types to get multiple features. And then from this one, we're going to take every extracted feature map, as it's called, and we're going to extract new features now. And then from these new feature maps, we're going to extract new features and new features and new features. So we're going to be doing this process, and this feature extraction, what happens here is I'm starting from an image, and I have multiple images. So to generate this, I apply convolution operator. We're going to talk about it. So a convolution operator, it's just taking an image and produce another image because it's a convolution. Right? So apply convolutions. I also reduce the size of this image. So we're going to see how to reduce the size. And eventually, after I do all these convolutions and I have all this spatial correlation taken into account, I take all the data and I create a huge vector. This is a process called vectorization. And once I get this very big vector, I'm going to take this vector and then I'm going to move the rest of the system like the examples I was showing you with the neural networks, like the standard neural network. So it's a vector. I connect this vector to another vector, and then to another vector, and to another vector, until eventually all my vectors end up to a small number of elements in the final vector that in this case corresponds to my class. So if I have, I end up with a situation where I have this four element vector at the end. This can correspond to 4 different classes, and I expect to have one in the node in the vector elements that corresponds to my correct class. Right, so this part here is the convolution and subsampling. Convolution because we generate the image, the subsampling because the size. And then eventually, when you stretch it out and you create it to a vector, this is called the fully connected or the multi-layer perceptron. And this sort of idea that you have this implicit feature extraction in the beginning and then you vectorize applies to the network and transform. So this idea is probably it hasn't changed nowadays. It's still the same idea that you progressively extract features through this process, and then once you have this feature extraction, you make them into a very big vector, and then you do vector stuff. You do inner product, you do similarities, you do stuff like that with vectors. And why do we do convolution on neural networks? Well, the whole idea is that if you take this image and you assume that you might connect everything to everything else, like a fully connected layer, then for every single location, I have to put a connection connecting every single location to every output neuron in this case. When I have convolution, because the whole idea of convolution is that it's shifting through the image, I can have one convolution together, one thing, one filter that I'm convolving, and then scanning through the whole image. So the whole image will be produced by sampling from a single convolution kernel. If I have multiple convolution kernel, fine, each one will scan the whole image and produce something else. This is extremely more efficient compared to having fully connected layer where if I have something in one specific location, it doesn't ever change compared to convolution where you scan. Right, so this is how the convolution layer looks like. So you start scanning the image. And once you start, for every location that you scan, what you do is you take the cells in the common region between the convolution that is moving, the convolution kernel that's moving, and the image, and you take the retrograde. And you get something like that. So you have an image that is convolved with another image, and it's produced another image. Okay, convolution between an image, the original image, and a very, very small convolutional kernel will produce another image. And they look like that. So I'm taking an image, I'm convolving it with that, this will produce another image. But I don't have one filter, I might have multiple filters, and every time I apply filters, I have multiple activation maps, as they're called, right? So this activation maps are for the convolution. So I have K convolutions, I'm going to have K activation maps. And each one of them will automatically try to capture something different about the data. Right? And this is the equation, this is the concept for the convolution. So when I say we're trying to capture something different, this is the process, right? So convolutions in the beginning will try to capture things that look like gradients and things like that. When you move up, when you move towards this part of the architecture, towards this, it's going to automatically extract more meaningful features. But again, you don't need to care about this. This is happening automatically, so you don't need to change anything to get this performance. Right, so what is the convolution neural network? What you care about is they care about, are going to find what's called location equivariance. So what location equivariance means is that one of the capacities of convolution is that if I have an image, and you imagine an image where there is a cat in the upper right corner, if I convolve it with a filter that is designed to find cats, regardless of where this image of the cat is in the image, it's always going to be able to identify this location because it's scanning the whole image. So the fact that things change in the image and you convolve with this filter and you proportionally change. So if I move my object to the right, the output of the convolution will also move to the right, it move up, it also move up. This is called spatial equivariance, and this is what's captured by the convolution, right? So this is why we convolution. Once you do that, we say like convolutional neural network, the parameters is number of filters, the size of the filters, the stride, the padding. How do I select one of them? Well, you take from the GitHub paper that you're using in order to start your work, and then follow this, and then you modify this in a trial and error way, right? So there is no way of saying, what, for your problem you need a filter size of 3 by 5, or for your problem it's 5 by 5. It's a trial and error always. So you start from a standard baseline, and then you potentially adapt that. But that's the idea of convolutions. And what's important, convolution is like, as I said, convolution is just scanning and taking the inner product, scanning and taking the product, which are all linear. So how can I make neural network work? I use non-linearity, which is this. So I take the convolution and then apply to every element of this convolution this activation layer. And this, for example, is one of the most interesting ones. the sigmoid. It's one of the most interesting because it can take any value and scale it to the range from 0 to 1. And it's fantastic because if you scale something to the range of 1, you can sort of interpret the probability. Because it's going to be positive, it's 0 to 1, but you find it's probability. So you can get this probabilistic estimation, we're going to see how it happens, through this sigmoid function. But there are others. And one of the most prolific part nowadays is what's called the ReLU. So a ReLU looks like that. It's just a system that is, if the values of this convolution are negative, make it 0. If they're positive, make them as they are. It's a simple thing. And this is sort of related to how the brain works. So what you do is you start from the image, you go forward, right? So you take a small region and take a data from that. And then you filter it through this activation. Go to the next thing. The same. If you want to produce multiple images, then what you want to do is you want to introduce scaling variance. That means if I imagine an image of an airplane, and the airplane might have the image like the airplane right in the middle, or the airplane might be somewhere like in the very up corner of the image. I want to introduce what's called scaling variance. So we need to identify these characteristics of an airplane regardless of whether it's in the middle of the image or the top right corner. So when we go to the force scaling variance, we do subsampling. Subsampling means you take the numbers, you group them together, and you give the largest number out of the group of 4, the average value, the smallest number, or something like that. Right? So you throw away. And there's again a motivation by subsampling, and it's mostly max pooling, the technique we're using. And as I said, you do convolutions, inner products plus the nonlinearity. Then you do this subsampling to make it smaller, and then you have smaller images, and then again convolution, and then max pooling, smaller images, and then again convolution. So eventually you're going to apply pooling, you start from the image with 256, it's going to come around 28, 64, 32, 65, 16. At some point, there's no information happening. So you start from the image with 256 or 256, and you eventually figure out it's like 6 by 16 pixels. These pixels values don't correspond to values or anything. They're more like features. So take this 16 by 16, make it a vector. Once you do it to a vector, then you can take these vectors and then connect vectors with other vectors to this fully connected layer. And what you do is you make sure that you put as many intermediate layers as you want, but the final one should be corresponding to the class. And as I said, the point here is that if you're trying to do classification, then the output of this is not going to be a zero like we want. It would be continuously valued number. So how do we take continuously valued number and make sure that the output is something which is like 0, 0, 1, 0, 0? So how do you do that? So you use this softmax activation function and you normalize that so that these values here, which are like any range, free range, it's in real numbers, they become constrained to be 0 to 1 and some to 1. Oh, now the output is the probability. And its node here corresponds to the probability of selecting this class. So there's a probabilistic interpretation of what the output of this system will be if you do this softmax function. Questions, comments, thoughts? Yes. It's big one. We typically use max pooling, but it's max pooling. Pooling in the sense that sort of tries to reduce the dimensionality of the data, but why not on the other? 9% of the paper is max pooling because it works better. Yes. No. In this. No. This is how we're talking about. This is the output we're going to see. The data is the convolutional neural network architecture we're talking about is going to take as input an image and it's going to produce a vector that corresponds to 0 and 1 wherever there is the corresponding classes. Right? So it takes an image and produces a vector and interprets this vector as classes. The example you're talking about is taking an image and producing another image. You can use a convolution and a deep learning architecture. It's not a CNN, you use a UNet. We're going to see it later. So there's a different architecture that goes from images to images. This goes from images to classes. So if let's say that what would be fantastic for me as a take-home message from this discussion today is like understand which network is good for what. So if you have an image or like 2D data or 3D data, and when I output, associate this the whole thing with one specific label, one specific class, this is the scenario I need. Right, so I'm taking the image, it may be 3D because I have like spectral bands as well, and I'm trying to identify a vector. And, this has this notion of a vector where everything is 0 except one where it's the correct value that I'm trying to find. If I'm trying to find something else, we need a different architecture. So, for example, this case, LNN, which is one of the first deep learning networks, and let's say the most standard architecture. You take the image, you apply convolutions. So what it says here is that you're going to take a 32 by 32. You're going to convolve it with regions with kernels which are 5 by 5, and you're going to each time you do this convolution, you're going to produce something which is 28 by 28. Why? Why do I go from 32 to 32 times 32 to 22? Why? Why not 32 by 32 again? It's a convolution, and the convolution is 5 by 5. So when you have a convolution between something that's m and something that's n, that was m plus n plus minus 1. So this spalling, so this is spalling the full idea that there are some things that fall outside. It's going to constrain my system to work on a smaller unit. So I take a 28 by 20, and I do it 6 times. So I have the 6. Then I do subsamples. Every 28, 28 is going to be 14 by time 14, and I still have 6. So for every one of them, I'm going to create 16 different new kernels, right? So you see, I'm going from 1 to 6, then to 16. So I play 16 kernels, but they are smaller images. Again, eventually I'm going to come here. At this point here, I have 16 times 16 feature maps. Each one is 5 by 5. I take them and I vectorize them. So 5 times 5 times 16 is the input here, and it becomes 120 vector. Vector, and then I take the whole vector and make it smaller until I hit the output vector, which is 10 elements, because this is classification in 10 digits, 0 to 9. So this is going to be 10. Yes.
That's like each convolution layer is something that's one kernel, right?
No. So when you define the convolutional network, you need to define one of the things that one of the parameters of this is the number of filters. So you define where you have 32, 64. So this here with 36, we're going to see programming how that looks like. In this case, this is 6, and then it becomes 16. Yeah. It's 6 and becomes 16. So this is the number of convolutional kernels I have, which corresponds to the linear activation function. Yes.
And the inputs size, what are claims here about it? When we go to space images, detect object, how you can change or can choose this style?
So typically, what you do is you assume the size 256 times 256 pixels, and then you apply the process of this. Now you're going to have a very big tile. It's like 5,000 times 5,000. Take each small part and apply your process independent or in parallel, but like by itself. So typically, the image is to get things working. It's like typically 256 times 256, or half of this, 108. Some data sets like that are very small, but it's the exception. The standard thing is like if you go now, one of the standard data sets that you use for classification in remote sensing, the image is most likely is 256 times 256. If it's a bigger region, just crop 256 by 256. Right, so this is from 98, and this is from 2012. This is the whole thing that started it all, which is again the same thing, like convolution, max pooling, convolution, max pooling, convolution, max pooling, flood them, make them into a vector, and then continuous. And this is the paper that sort of changed the whole thing, right? So this is the ImageNet winner competition in 2012. Similar idea to this one, it's just that this was implemented in the GPU, so it was much faster. So it was much bigger. So it was fantastic in this type of network. And then from then on, so maybe we do it more complicated. So let's put, triple layers, or for example, this one has 64 convolutional layers that becomes 128, and then 512, and so like a huge number of convolutional filters. And so that was the BGG, and a lot of convolution there, very deep architectures. And the question like, okay, so why am I doing convolution with a size of 3 by 3? Maybe my solution should be 5 by 5 or something else. So in Google, someone was watching the movie and said, you know what, I'm going to do all of them. So they do all of them. So this is the essential architecture, which is similar to what we see before, but instead of saying, you know, my convolution architectures are going to be one type, we say I'm going to be 3 types. So we have convolutions of 3 by 3, 5 by 5, and 1 times 1. So point-wise convolution. And move on. This, I think, is one of the most interesting novelties that happened with this new era of learning compared to the standard architecture, which is called residuals. So the whole idea of residuals is that what you do is you take the input and then you bypass part of the convolutional neural network and you add this input to the output of this processing. Right? So a lot of discussion why these things work and why it's good, but it's working and it's doing. And one of the standard things that we're going to be using as a deep learning model is what's called as residual network, which is this architecture here. And this allows us to become very, very deep. So by using this idea of skip connection, as they call, they were able to reach neural networks of 150 layers. Right? So very, very, very deep layers. It's not trivial to have a neural network with this depth. So if you have like able of enhancing the depth that get very big, a very deep neural network, then you have significant gains in terms of performance. So this ResNet is, let's say the off-the-shelf standard convolutional neural network for image classification. Today, you're going to get off-the-shelf in TensorFlow, you're going to get a ResNet. ResNet is the standard. Other people, keep on moving. So there is, for example, this ResNet that sort of pushes this residual connection to the top level by connecting everything to everything, and you overload the system, but it's still able to produce, which is fantastic. This architecture, the unit, is something that is very interesting, and this is something that comes to the question we talked about before. So these architectures here, you end up with a fully connected layer at the end, and this fully connected layer at the end will be associated with the classes, right? So you have 100 classes, so you have a vector with 100 elements. What happens if I don't want to have an image and I extract this? So you have different architectures that go from images to images, right? So this is the unit architecture. So the unit architecture, it's called unit because it looks like a U. So what it does, it takes an image, progressively shrinks it down until you get to this bottom-left layer, bottom-left layer, and then you start expanding it. And we're going to see example of this. So this idea of compressing and then expanding is been instrumental. And what you get is, you get from an image, so this is 572 times 572, to an image, right? With potentially different size or potentially the same size, but from image to image, and we're going to see examples of where unit is applied. Right? So these are the standard techniques that we use. We want to have an image and we want to classify it. So if you have an image and you want to associate this image with labels, try a convolutional neural network. If you have an image and you want to associate this image with another image, try a unit. Questions, thoughts, ideas? So these techniques now, convolutional neural networks, when you have a single image, what happens if you have time? As I said, we have recurrent neural networks, and these recurrent neural networks is good for like video sequences or audio or text, maybe with back. And the whole idea is that you formulate the problem like that. So instead of having a feed-forward neural network where they have the input, hidden layers and output, the hidden layers are being preserved as you have the network. So the hidden layers are indexed with T, which is time. And so this is about the whole idea of memory. So I get an input at times T, I do something with it, and produce something else. If I go and produce an input at xt plus 1, I'm going to have a new thing here, which is ht plus 1. And I'm going to be producing something else here. So this idea, this is not fixed in time, but it sort of captures the whole idea of time of sequences, is what the recurrent neural networks do. The whole idea is pretty similar. So it's just like linear products again. So nothing like too dramatic. It's just that those are indexed by time. So there is this propagation through time technique. But it looks like that. So you take an input, this input sends hidden units, and the outputs, and these hidden units are updated based on the previous values, right? So again, look, there is a lot of discussion of how things work, but we're gonna sort of skip the details and stick to the idea that recurrent neural networks are fantastic for encoding time. And when you try to train this neural network, you still use the standard techniques we know, standard optimization techniques, so nothing changes. And the whole idea is that you do this backpropagation over time. So whenever you have an output, you sort of propagate it through the network itself, but also through previous instances. Again, you don't need to know exactly how it happens in the sense that it's being abstracted in the software now. You can like use an RNN and move in, but this is what the major thing that's happening. And yeah, there are some issues with RNN like vanishing gradient and so forth. Yeah, let's move on. And the last thing of this neural network, recurrent neural network, is this LSTM. And so this is the LSTM architecture, which again, it's an off-the-shelf you can use now. It's more complicated. Now, I'm not going to go and bother and explain why everything is what it is. It's just that people decided that this one over here was not complicated enough. Let's do it more complicated. Why exactly do I put this feature vector here and does that? And zero idea. And nobody does. Like, why? But why put the darn nature or put something else? People just try trial and error, and it's like it's been working, and there is some assumption about the hidden stuff like that. But there is a lot of hand waving about how we design this. Very sensitive about LSTM. But still, that's a lot there. And the last thing that we're going to just mention, but not talk about, is what's called a transformer. Or division transformer for the case of images. So, whereas in standard convolutional neural network, we take the images and we convolve it, and the idea is that we look for this convolution for seeing the stuff. In division transformer, you take the image, whatever that may be, and you split it in parts which are completely disconnected. And so you throw away the idea of spatial smooth and stuff like that. You just throw it in different parts, and then you take each one of them independently and throw it in the neural network. And this neural network, because it's working with this massive amounts of inner product, it's going to be able to identify correlations semi-magically. Right? So nobody knows exactly why this thing works. And the fact that you throw away some of the manual assumptions that you have, like spatial smoothness, you throw it away, it's not really effective. But if you throw like transformers, which is a keyword, another keyword which is the underlying idea that's happening inside, and you might hear this what's called attention. And attention is this technique that is being introduced there that sort of makes the system focus on a specific instance. And this is mathematically described, it's just another inner product, but it's called attention. And it's important because the very first paper that came out of transformers was like what's called attention is all we need. So attention, the whole idea of how attention is a thing in learning, but that's a very fun story. Yes.
Is it related to how the CNN works? The idea of embracing image
No. It's operating on inner product, so it's not filtered. So convolution, you take convolution, I say forget transformers. Okay, so as a signal processing, I understand what's happening. Now with this inner product, why this inner product and how scaling this inner product gives you attention, why this attention is important. People have ideas and try stuff, but this is performance driven. So you see fantastic performance. This is what so ChatGPT T is transformed. So it's a very ubiquitous architecture. But why exactly does it do that? And what it captures, it's first we see that it's working, and now we're trying to understand why. Yes.
So I wonder about the repeatability of machine learning models, especially for nonsense. With your experience, have you, if you go and use some machine learning model from a certain paper, like with your experience, have you seen that it's repeatable, at least in remote sensing for geoscience applications?
Okay, so repeatability in the strictest sense, in the sense that if I run this algorithm 10 times, I'm going to get different results. No, it's completely deterministic, right? So the algorithms are fixed. what you're referring is most probably the idea of generalization. So I have a system that is being trained, and I believe the guy that wrote the paper and the code there, and on this data set, it's fantastic. But then I take this and I take the same observation, but it's from the neighboring region, and it fails. This is something that still happens, and it's a problem. You can combat it with more data, but what does it mean more data, and when is more enough? But it's a problem, and I've seen it. I've seen it in situations where it was fantastic in one situation, and you take the same code, and it's really bad at something else because it wasn't able to capture that, or maybe it needs more data, or maybe something like that. So, but this happens. But this is the problem of generalization. So this is the holy grail of deep learning. So the holy grail of deep learning is a system that can generalize. So learn, make the thing that you like to understand simple, but not simple. So get all this information to a simple model, but make sure that this simple model is enough to do my job. So not make it simpler. So this idea is the generalization, which is an open topic for remote sensing, for machine learning, for AI, for the whole community. It's not our own. Yes. Excellent point. So there is the version of ConvLSTM, which provides convolution LSTM. So you have images, so you use convolution because it's images, but then I got memory stuff happens over time. So there is something we're going to talk about it that's called ConvLSTM, and this is the captions both of them, spatio-temporal evolution, which is for us, for our community. This is there is this paper called ConvLSTM, another paper that we wrote that has a similar idea, and not that many more, right? So for the community of remote sensing, where like analyzing spatial-temporal data is like the bread and butter, because it's not the bread and butter of people doing natural image understanding, there hasn't been sufficient success there. So there is this ConvLSTM, another technique that we wrote, and that's it. Whereas these scenarios of convolutional neural network is not the tip of the iceberg, it's the tip of the iceberg. There are like thousands of techniques and architectures. But for our case, where you have more specific data in remote sensing, still definitely a lot of space to do stuff. Or a couple of hints, right? So if I got a lot of data and my system is overfitting, right? So it's learning a lot of, it's doing excellent job with the data like that, but then I put it on the testing data and it's not working. What can I do? Drop out. So this is the standard technique that's already part of the library. And what it does is effectively it goes and zeroes out some part of the connections during its iteration. And this allows the system to be more generic, right? So if, for example, I have a neuron that is becoming too much focused on a specific characteristic by throwing away during this thing, I make the system be able to distribute this representation. This is what's called distributed representation. So not have all the information, not capture the fact that like airplanes have wings in a single node, because this would be too specific. And if I see an airplane from a different angle where I don't see the wings, I'm going to fail to identify it. So generalize it through this dropout. And there is one parameter which is called a dropout rate, right? So how many things you want to throw away during its iteration. And this happens only during training, right? So once you're done, you have a network that is fully connected, all these weights are there, and that's it. Right? So this is only during training. There is another version for testing we're not going to talk about. Another key option when you design is what's called budget normalization. I'm not going to go into details. In fact, what you do is sort of C-score, normalize some intermediate features. You see the option, budget normalization, give it a try, maybe it helps, maybe it doesn't. What is, though, extremely important is the whole idea of transfer element. So this is the situation. You have, fantastic data set of images of, like whatever, elephants and animals. And I train my system with a lot of time, with a lot of resources, with a lot of money, and my system is doing a fantastic job. But then it turns out that my problem is not associating images, but like analyzing MRI or remote sensing. Can I use information that I have from this part of the system to do a better job with this one? So this idea of having a system that is trained on a similar task, or not the same task, right? So these are images of animals and identifying animals. it's similar in the sense that it's similar as a file, but it's what it is in domains. Can I use this and leverage this? So when I go to a new domain, when I don't have a lot of data, I can use this pre-trained model and then fine-tune it. So use a small number of data that I can provide and make sure I get performance. And this is one of the most fundamental aspects of deep neural networks. So in GPT, P is the pre-trained. So GPT, P is the format, P is the pre-trained. So this process is pre-trained. So what you can do now is you can take another cell of a neural network that has been trained on millions of images, blocks and whatever. Say, you know what, take this, and I'm going to have my 20 images of oil spill from Sentinel-2 and train my neural network only on these 20 images. If you follow this transfer learning approach, then you can see significantly larger number of sustained performance, right? Whereas if you don't do that, the performance goes down very fast with the number of examples. So the whole idea here is like a lot of material just to tell you that if you can exploit this fine-tuning, do it. So one of the ideas that I have the network and I train it on similar task and then I apply it on my own task. And another idea is what's called node distillation, where I have one neural network being trained on one task, and then another neural, which is called the teacher, and then another neural network, which is called the student, try to sort of approximate this teacher, right? So this teacher is fantastic and classifying cats and dogs. Now I'm going to give the small one that's going to be trying to do whatever task is I'm trying to do, classify remote sensing images, but somehow constrain it with respect to the pre-trained teacher model. Just keep in mind this idea of knowledge distillation. It's being very active, use it. It's not as prolific as transfer learning, but it's there, so keep that in mind. Okay, so we're going to start seeing some like specific applications of remote sensing, but eventually we'll go for the large break. Right, so as I said, application of remote sensing. You have satellite images, neural network, and try to predict. So what type of problems, right? So you have this is called semantic segmentation. You have an image and you try to associate every pixel in this image with one label. So this is segmentation because you do it on every pixel, and this semantic because it has to do with classes, right? And then you have detection and localization, which identify this. You have another detection, which is a multitask detection, and then you have a situation which is called an instant segmentation. So not only identify that this is a dog, but identify that this is dog number 1 and this is dog number 2. Or in the case you remember the case with the boats, this is boat number 1, this is boat number 2, this is boat number 3. Which is called this segmentation. The very standard thing we're going to do in remote sensing is do multiple classification. So you're given images like the data set I showed you before, with airplanes and harbors and intersection. Try to make a system that's going to put them, in the appropriate region. So whenever I have a new example, it's going to fall where I want. Typically, neural networks that do that look like that. So convolutional. So this is another visualization. So it's a convolution, max pooling, fully connected, softmax. So the standard 4 layers we saw before, many of them repeated. That's the standard detection. Now, this plot here is the performance on a specific data set called UC method, well-known method, on classifying the image. And these are different deep learning architectures. And this is the performance, so this is 80% rating. And what you see here is performance, 97%, 99, 98, 98, 96, 99, 98, 99, 99. So what does this performance tell you? If you see the performance, it's like 99, 98, 97. What do you think? Oh, great, that's another problem. I'll dig my hands into it and maybe get a nice paper. The performance is already saturated, it's 97%. So what I'm saying that this problem is solved. So take any of this convolutional neural network, apply this problem is going to get 99% accuracy. Like the stuff, the extra stuff that doesn't have percentage is noise. It's just prediction noise. So it's saturated. So this problem is solved. So you have a image, and that's the image. And we're going to classify this in one class, so using another, it's solved. Use any of the convolutional neural network, even something like that. So what do you mean? It's like going to 1997. And I can get at least a paper out of this. So that was real. It was like silly, you know. I assume that was like silly. So, as I'm trying to say that, now, like 2023, July 2023, the standard setup where you have a standard 80% of the data you use for training, 20% for testing, and you want to classify image, you want to CNN, it's done. Right? So use any of them. It's going to be fantastic. But that doesn't mean that our job is done. Right? So this is a very specific, nice, calibrated, and very similar to computer vision. So you have an image, assign one label. Right? So this problem is done. But there are extremely big number of different variations of problems that are not done. Right? So for example, you have multi-class versus multi-label. So in this situation, we have a multi-class. So you have an example, you decide whether it's class 1 or 3, one of them. In the multi-label, you can have different combinations. So in this situation, we move from data sets which for the same image you have like representation to things like look more like that, like airplanes and cars and papers. So you have a more holistic description, a more semantic description of the data. Right? So instead of having a single class, you get the multi-labels. You go multi-class, multi-label. So the problem is not there. I saw one of the things that we did a few years back, so we should have located now that was back there. Is we using a label like that, and then for each specific label, we independently identify whether this label should be present or not. Right? So there was a variation of the convolutional neural network, so this is a convolutional neural network, convolution, pooling, blah, blah, blah. And then we were able, like 4 years back, to do something open by saying that take the standard architecture and now make sure that the output is not selecting one out of A, you can select many, and you select them independently. Right? So the output, instead of giving one and everything else, it will be like that. And that was a new thing, right? So that was a new paper, that was over 3-4 years back. There are other techniques that probably can do that better, but so you need to always think about what's the there. So that was beyond 3-4 years back. Even segmentation, right? So you have an when I identify, as we said before, so this is another segmentation. I think the conscious community does the data fusion challenges every year. In many years, very similar to this. So this is the segmentation. So you give assigning pixels as a beginning, and so forth. The standard technical use for the segment. So this is how the segment looks like. It's a bit old, but it's been very, very consistent. So convolution and pooling. So convolution, fast normalization, and this a lot of integration function. Pooling, the inverse of pooling is subsampling. This is softmax. So by now you should be able to fully interpret this view. We talked about this what convolution is, yes. Fast normalization is something you do there, but it's fine. Pooling, yes. Softmax, yes. So you understand how you can put these blocks together and come up with this. This is called the hourglass architecture. So it's bigger and that's smaller than pixel again. Take a need to be much standard GP and you do a segmentation out. So this is a map. So the border where every pixel corresponds to one class and this class corresponds to the border. Yes. You really need to put some effort on it. So you have this sort of very nice part of the that's what the bottom don't it's fully connected. Effectively, that was published in 2017. If you want to do something segmentation today, use QNet. So I say that for historical purposes, but nowadays QNet. An example of this is QNet and variants of this QNet. But that is the same idea. And for example, why I say QNet. So this is we're trying to find the system, and I'm going to say, okay, so we're going to do extreme event detection. So we have satellite, and then we're going to use annotations from users in the emergency services of the European Union government service, so the emergency, so people delineate plans and things like that. So my input is satellite, my output is all the stuff that people put in creating these delineation maps. Can I use this input and start with the yes? So what do we do? So we run a Okay, good training network, what the input is satellite input, and the output should be maps, which is like 0 and 1, whether it's, for example, in flooding, whether it is flooded area or a not flooded area. So that's my input. I can come up with a network to do this. Before I come up with a network, I need to come up with a data set, because unless I don't have a data set, I cannot train. So generating data set. So you go and you take the process of the relation center towards one, you go to the correction and everything, and then you find emergency services respond that are hand-annotated, you over Excel, you put them together, it's like this is my data set. This is my input, this is my output. So I know what I'm trying to do. And it's like, so this is my input, and this is my output, right? So Sentinel-1, radar, and Sentinel-2, before and after. And these are segmentation maps that are produced by human experts that do the segmentation map. Okay, so my input is what is the neural network that I'm going to use? It is going to be a ResNet. No, it is for things that end up labels. So what is the technique that I'm going to use when I have an input image and output image? A unit. Fantastic, units. What is that? It looks like that. Which is similar to segment, but similar idea. And yes, convolution, max pooling, sigmoid, and then upsampling, which is the inverse of max pooling, just making everything twice. So I have my input, I have my output, I have my network. And that's it. I can write my bank. What we saw that we said things like, okay, but this is fantastic, but let's take a single image, right? So I have two satellites and two time distances. Which one is this? Okay, so can I extend this unit so that there's two time distances? Yes, no problem. You just modify this unit, so you sort of split it in two, which is extremely easy to do programmatically. There is no significant theoretical computation. It's not like I need to solve any optimization, just design it. And then I can modify this and have an end-to-end trainable system that takes two inputs before and after event and produces one map. So this flexibility that we have with deep learning, that we have one or two inputs or one modality or two modalities, and just modify the code and make sure the system works, you cannot find it in any other solution. Right? So 3D unit in the sense that I have like two instances, but now it's a one modality. Can I do it 4D? Yeah, sure. Now you can have a system that takes before and after images from one satellite and before and after images from another satellite. Simple modification of the neural network architecture is extremely simple. Clear motivation, I will use them. Not very solid mathematical understanding. It's not like this is gonna, find some features and some frequencies that are not present and everything like trial and error. But take the network, modify the system to fit your problem, and then you have fantastic performance. And I mean, this is interesting because let's say we measure this performance from the IOU, right? So which is a metric that says how well I can segment my images. And what we do is so what happens if I segment based on specific values? Well, it should go to up 1, not that good. What happens if I use an SVM? Not that good. What happens if I use this unit but a single input? So 57% and 54. It's okay, not that good. What happens if I use two time distances? Well, especially for the Sentinel-2, it goes from 54 to 64. So two time distances is good. What happens if I use two time distances and two modalities? It goes to 72. So you can see how progressively making my network more complicated with nothing fancy, like it's just guided by my intuition. I make my network just a bit more complicated, and progressively still the monotonic increases performance. Yes, now it's getting better. Right? Yes, now if I have this is better than any other case. Right? So using all the available data is, so let's say the manual is like use all the data you have, right? So if you have like different modalities, different time instances, different, take everything, be sort of sensitive in how you integrate them together, but throw all the data you have at once. And you get performance look like that, right? So this is like other techniques, and this is what the ground truth. It looks really like simply it's a modification of the unit. Nothing too fancy. Lunch break. Okay, so let's have a lunch break now. We're gonna wrap this up and do the example once we get back. Any question? Yes.
Dropout, is there a way of proceeding with connection to dropout, or is it
No, it's stochastic. And that's the whole idea. It's stochastic. Here is the percentage of those that are going to be connection will be equal to 0 at every iteration. So there is a number from 0 to 1, and say, you know what, 20% of the connections throw them away. But this becomes stochastic. There is this. Okay, so that's great.
Yeah, thank you. I see.
What?
I assume it's working now.
Do something?
That's